Hello, thanks for clicking. Welcome to another Nargilus 2 production. Today we're going to be learning about Euler's method. Okay, it's a numerical method that you can use and to approximate the value of a function using tangent lines. So let's take a look, see how this works, and we'll go from there. So again, Euler's method is a numerical method that's used to approximate solutions to a differential equation using tangent lines. All right, so let's say I had a differential equation, whatever it might be. Let's say something simple, dy dx equals x plus y. This is not a separable differential equation. And if I asked you to find for me, let's say f of 1, well, you couldn't find f of 1 because you can't solve this differential equation, right? So since you can't separate it and solve it, there's no way to be able to find f of 1. But obviously, we do know that we'd use a tangent line to approximate f of 1 if we wanted to. So let's say that this is my curve here, f. And on f, I picked 0.5 as a point of tangency. And I drew a tangent line to the curve at 0.5. Okay? So I could use this tangent line to approximate f of 1. But the problem is, the further away you get from the point of tangency, the worse that approximation is going to be. So if I approximate at 0.5 and ask you to find for me the approximate value for f of 1, it's not going to be a great approximation because 1 is pretty far away from 0.5. So the idea that Euler had is he said, what we're going to do is this. What we're going to do is we are going to take steps along a tangent line. So for example, let's say you built this tangent line at 0.5. Rather than find the value for f of 1 using this tangent line, instead you're going to take a small step closer to 1, but you're not going to get to 1. So let's say you took this small step, and we'll call it h or delta x, I guess. Delta x, I guess, would be good. All right. And let's say you went to 0.75. You took half a step. Okay. So now you found the value at 0.75. And then what you did is at 0.75, you built another tangent line. So you built a new tangent line at 0.75 to the curve, which I guess would look something like that. Okay, and then you said, all right, let me use this tangent line at 0.75 to approximate f of 1. Well, that approximation will be better or closer to the answer than the tangent line that you used at 0.5, right? Now, again, if you take a smaller step, you make more tangent lines, which means that your final tangent line that you use to approximate f of 1 will be even closer to the value of f of 1. And that's what Euler's method consists of, okay? It's basically hopping along tangent lines to get a better approximation for this function's value than what you could get using a tangent line approximation where the point of tangency is far from the value you want to approximate. All right, so let's see how this works. Let's see how it works in practice. Let's see how we can find these values. We're going to do it a little bit differently than actually go ahead and find the equation of the tangent line, I think. There's a couple ways you can do this. One of the ways you can do it is to find the equation of the tangent line for each one, but I'm going to do it a little bit differently, which I think is a little bit easier to understand and see what's kind of going on. So let's let y equal f of x be the solution to a differential equation, dy dx equals x plus y, with a given initial condition f of 0 is equal to 1. I want you to use Euler's method, 2 steps of equal size, to approximate f of 1. So if I tell you I want you to use Euler's method, then I have to tell you 99 times out of 100 how many steps you're going to take, and that more than likely they'll be of equal size. They don't have to be, but most of the time they will be. And I want you to approximate f of 1. So what does that mean for me? If I'm going to take 2 steps of equal size to approximate f of 1, I'm starting from x equals 0. I'm going to end up at x equals 1. 2 steps of equal size means delta x would be 0.5, right? So literally, Every time I change x, I'm going to change it by 0.5. That way I'll take 2 steps, and I'll end up at 1. All right? Okay, so to do this, what I do is I tend to set up these little charts. In the chart, I start at x comma y. Okay, and then what I want to do is I have my delta x, or my dx. All right, in this case, we already know what dx is. Dx is 0.5. And then we're going to calculate dy dx, x plus y. All right, we're actually going to calculate that value using our initial condition. Okay, and then from there, I'm going to calculate dy by taking dy dx and multiplying by dx, right? Think about it. Take a look. Dy dx times dx is dy. And then finally, I'm going to take my point x and add to it the change in x. And then I'm going to take y and add the change in y. And then I'm going to start the process all over again. All right? Okay, so let's see how this works in practice. My original initial condition is 0, 1. The change in x is 1/2. We'll do it as a fraction, I guess. Dy dx is x plus y, so that's 0 plus 1. That's 1. Dy will be dy dx is 1 times dx, which is 1/2. So that's 1/2. And then x plus dx is 0 plus 1/2. Nope. Yes, 0 plus 1/2. And y plus dy is also 1 plus 1/2. So that will put me at a new point. Let me go over here and erase this. That way we've got a little room to write it. So that'll put me at the point 1/2, comma, 3/2. All right, and now I'm going to start again. I'm trying to reach f of 1. Okay, so I'm trying to make my x value 1. I need to know what the y value is when x is equal to 1. So I'm going to start again now when x is 1/2 and y is 3/2. Dx is still 1/2. You're taking another half a unit step. Okay, dy dx is going to be 1/2 plus 3/2. So that's 4/2. That's 2. So dy is dy dx. That's 2 times dx. Dx is 1/2. 2 times 1/2 is 1. So now we have 1/2 for x plus dx is another 1/2. And then y is 3/2. And then I'm going to add to that 1 more. So that gives me 1, comma, 3/2 plus 1 is 5/2. And that's it. You've reached f of 1, an approximation for f of 1. So f of 1 is approximately 5/2. And that's the answer. Okay? That's how this works. All right? All right, let's try another one. Same concept. Let f be the solution to the differential equation dy dx equals x plus 2y. And same initial condition, 0, 1. That's okay. It doesn't have to be 0, 1. In this case, it happened to be again. Use Euler's method with 2 steps again of equal size to approximate f of negative 0.6. So now my delta x or dx, I'm starting from 0. I need to end up at negative 0.6. So I have to go down by 0.3 every step I take, right? Or down by 3/10. Okay, maybe it'll be easier to do it with fractions. We'll see. All right. Okay, so that's fine. You can increase or decrease to reach that approximation value that you want to have. All right, so we have x plus y. We have dx. And then we know dy dx is going to be equal to x plus 2y. dy is equal to dy dx times dx. And then we have x plus delta x and y plus delta y, or x plus dx and y plus dy. All right, so here we go. So we're starting from the point 0, 1 again. Dx is negative 0.3 or negative 3/10. I think it's going to be easy. I don't know. It doesn't make a difference. So dy dx is equal to x. So that's 0 plus 2 times y, 2 times 1. So that's 2. dy is dy dx, so that's 2 times dx. dx is negative 0.3. That's negative 0.6. Okay, so x starts on 0. It goes down by 0.3. And y starts at 1 and goes down by 0.6. So now I'm at the point negative 0.3, 0.4. All right. So now I'm going to try again with negative 0.3, 0.4. So dx is again negative 0.3. That will reach me to negative 0.6. That's where I want to end up. All right. And then dy dx is going to be x plus 2y. So that's going to be negative 0.3 plus 2 times 0.4. So that's 0.8 minus 0.3. That's 0.5. So dy is 0.5 times dx, which is negative 0.3. So let's see, that's negative 15, move the decimal 2 places, negative 0.15. So then I'm at negative 0.3. I'm going to go dx, that's down by 0.3 again. Y is right now at 0.4, and I'm going to go down by 0.15. That puts me at negative 0.6. That's where I want to be. And negative 0.4 minus 0.15 is 0.385. Right? Yes. Or 0.385. So then f of negative 0.6 is approximately 0.385. And that would be my answer.